So this is the fourth recitation, and today we're going to talk about some LQR stuff, get into some of the terminology, talk about how we can use a coordinate change to make the LQR policy a little more useful. And then we're going to talk about how we can extend LQR for nonlinear systems and how this actually works super well in practice. So I know today was a weird, or this week was a weird week because we only had lecture on Tuesday, not Thursday. So I have, less material to kind of go over now. But one thing I think is important is to go over the LQR terminology, because there's a lot of different LQR flavored things that we're going to do in this class, and people often have trouble kind of placing them with respect to one another. So I'm going to do a very general kind of LQR roadmap. And so we have, let's do this right here. Let's do LQR roadmap. And it's going to be important not to mix these things up because they are all different, but they definitely seem similar, especially when Zach's talking about them. So the first thing is that I'm just going to do discrete only. So discrete only, I'm not going to do any of the continuous time stuff. Everything that I'm about to write out has a continuous time version, but in this class, we're much more focused on the discrete time stuff. So the first thing we'll do is the thing you saw on Tuesday, and this is going to be finite horizon LQR. So this is the following optimization problem. I'm minimizing x1 to n, some n number of time steps, u1 n minus 1. And my cost function is the following. I have a sum I equals 1 to n minus 1. And this is going to be 1/2 xi transpose q xi plus 1/2 ui transpose r ui. And then we have this terminal cost here. So everything here is within this sum, and then this is not attached to the sum. And this is xn 1/2 transpose qf xn. So here's our stage cost. These are kind of what you'll see thrown around. Stage cost. And this is terminal cost. And it's common to have different cost matrices for the stage and the terminal costs. So since we have one more state than we have control inputs, since what we're doing is that we're saying, xi u of I gives us the next x, xi ui gives us the next x. We keep doing this recursion kind of thing. We're going to have one more state than we have control inputs. And so I'll kind of spell this out in a very Markov process looking way. I'll do the following. So we say is we have x0, u0, and these kind of come together to give us x1. And then u1 and this come together to do x2. And normally there's the control input could be motivated by the x's. But the idea is that I'm going to keep doing this until I get the following, until I get x n minus 1 u n minus 1. And this is xn. So this is just like a rough explanation as to why we have one more state than we have control inputs, is because the way we've structured our dynamics, we're doing this, and sorry to keep moving this stuff around, but move this down a little bit. Is that we're doing this whole thing where we have x of k plus 1 is a function of xk uk. I'll make these dots actual dots. And so the idea is that we have one more state than we have controls, because we need a control to get to the next time step. But then at the last time step, I'm just going to take one more step. I'm going to go to that final x, and then I'm done. So everything you're going to see in this class, we use a discretized model with an explicit integrator. So integrating things like this, we're always going to have one more state than we have control inputs. And so this kind of tripped me up at first, But I feel like once you kind of think about like the Markovian structure of this process, that this is a Markov decision process, and think about it in terms of like kind of this graph structure of takes a unit x to give us the next x, and we just do so until we get to the last state. So coming back to this, we're minimizing over x's and u's. We explained why we have the number that we do. I'm going to have a stage cost. It's going to be applied at every single x and y with the exception of the last one. And that last one, I'm going to have a terminal cost. So the constraints subject to some initial condition. So I have like some initial x that I want to start at. And I'm saying this just for, this is not actually how we solve this problem. This is just how we would describe the problem. And then we're going to have x k plus 1 equals a xk. And I'll be a little more general. So I'll do time varying. So what I can say is I can have a new a and b for every single time step. So the dynamics don't have to be the same for everything. xk plus bk uk. So here's kind of the first LQR problem that we'll learn, is that we have this nice quadratic cost function and linear dynamics. And so the two quick assumptions that we'll talk about is I need Q. I'm going to write this out in two different ways. I'll write this out. The first way is that I of Q must be greater than or equal to 0. And I of R must be strictly greater than 0. And you'll see this also. Q and this weird thing right here, and then R. It's basically like a greater than sign with like a little more shape to it, is how I like thinking about it. So all this tells us is that in order for us to set up this LQR problem, Q and R have to be symmetric, positive, semi-definite. Sorry, Q has to be symmetric, positive, semi-definite, and R has to be symmetric, positive, definite. So no matter what, even if it's convex or non-convex, these terms will always end up being symmetric. And what we're saying is that for Q, the eigenvalues must be greater than or equal to 0. So it must be a convex quadratic function. And for R, all the eigenvalues must be greater than 0. They can't be equal to 0. And this is kind of how we write it out in terms of, what you do like in a programming language. And here's like the mathy way that you'd see it written out. So this is the LQR problem. And the idea is that like this is basically the best of everything we could want. We have a nice quadratic cost function, which is convex. Then we have easy linear equality constraints. So of the convex optimization problems, this one is like the second easiest to solve. I'd say the easiest is if there's no constraints. If it's just an unconstrained quadratic, then I just solve a linear system for the gradient being equal to 0 and I solve it. If I have constraints, all I do is I write out that KKT system, and again, I solve one linear system and I solve this problem. So as far as like setting up convex problems to solve goes, this is far and away like one of the easiest things we can solve. So this is, and I'll write the name for this. This is finite-horizon LQR. Now we're going to talk about infinite-horizon LQR, which is, as you're seeing, because I'm making a pretty big copy of this, it is basically the same thing with one key difference. So the difference that we'll see is just going to come from this index. This is going to look kind of silly for the time being, but I'll say from x equals 1 to infinity. This is just forever. And then you'll do infinity minus 1, which we all know is not anything real or tangible. But the idea is that I'm now optimizing this cost function where I just say, I'm not looking at a finite history of 10 time steps or 100 time steps. I'm looking at from here to the end of time. So as you imagine, the finite horizon LQR problem becomes the infinite horizon LQR problem once n exceeds some huge value. And in practice, this value ends up not being that big. It's dependent on the dynamics of the system and what your time step is. But normally for most robotics problems, maybe 10 seconds is like a reasonable point where like it will now become just the infinite horizon problem. And this is infinite horizon LQR. You will also see this first one written the following: time variant LQR. This is what Zach calls it, and you'll see this because what we talked about is that A and B, they can be different. Now that's another thing worth changing here, is that for here A and B can't be different. So for the infinite horizon LQR case, I have an A, I have a B. This describes my linear dynamics, and I have a Q and I have an R. And these are not specific to the states. These are constant throughout the whole process from starting now to the end of time. So to describe the infinite horizon problem, I just need A, B, Q, R, and that's it. For the finite horizon problem, or time variant LQR, I need to be a little more descriptive, or at least I can be a little more descriptive. What I can say is that I can now have a terminal cost that applies to the last time step and the last time step only. And then I can say that I have these linear time varying dynamics. And by that, I just mean that these A's and B's, they can be different for every time step. And this does not change how easy this problem is to solve. It's still just as easy to solve. So here are kind of the two LQRs that we were introduced to. And it's important to know that these are not anywhere near the same as iterative LQR, which we'll learn about in the next few weeks. So maybe you've seen this before. So iterative LQR is not this. It's very easy to confuse time variant LQR with iterative LQR because when you write down the math, there's some stuff that looks pretty similar between the two of them. But for what we're doing right now, don't worry about ILQR yet. If you've heard about it, great. But it's not that tied into what we're doing right now. So if you are trying to figure out like, well, which one of these is ILQR, it's neither. All right, so now let's talk about how we actually solve a problem like this. And I won't go through and drive what's exactly. I'm going to talk from like I guess like a higher level of what we're looking for. So when we solve control problems, we're looking for a policy. And what my policy is, you'll see it's written as like pi of x equals u. So I want some function that takes in the state and gives me a control input. And the idea is that on my robot and my controller is taking in a state or a state estimate, and it's spitting out a policy u. And so what I just showed up there is that these problems are convex. These are quadratic programs with equality constraints, which are convex. And this is our favorite problem to solve. So we can solve both these, or the first one. So this one, equality constrained QP, which we love. This is like the easiest thing to solve. So here's one thing I could do. If I wanted to solve a finite horizon LQR problem online, what I could do is I could make my policy the following. I could do pi of x equals solve QP, and then a 1 to n, 6 to minus 1. So this is what I can do. At every single time step, if you give me a state, what I'm going to do is I'm going to go back to this original problem. I'm going to form this optimization problem, and I'm going to say that the initial state must be the state that I was given. So my policy is going to take in this state, it's going to set it as the initial condition, and it's going to solve this optimization problem. And every time it gets a state, every time I call this policy, it'll set up and solve a new problem. This is a totally correct way to do this. But this is also a super dumb way to do this, as we'll soon realize. So this involves setting up and solving a convex problem, which is something that we're happy to do. Like we do this in like all MPC controllers that you'll see. But it's totally unnecessary in this case for the following reason. If we solve these things like a QP, what I'm doing is I'm explicitly optimizing over the X's and the U's. And what Zach showed us is that we can use the Riccati recursion, or we can use the sparse matrix tricks. And because these problems had this special structure, we figured out ways to solve not just for a nice convex program that we solve for this policy, but we've actually solved for a feedback policy. And what the feedback policy says is, I'll give, like, here's two options, option 1 and option 2. Option 2 is just the feedback policy. And this just tells me the following. I solve for some k's, and I now just have a feedback policy where I have a bunch of k's and I get an x, and I just throw that x in there. So as you can see, doing matrix multiplication is much easier than doing and setting up a whole convex problem. But also it gives us another great thing where if the x change, my feedback policy is just going to update automatically, right? So I can have noise on my system, and we'll see an example of this. So imagine if I had like a 2D space. So this is my state space. I have like the example Zach gave in class. I have a double integrator, which is kind of like, imagine a hockey puck like sliding on ice. And what I could say is that I have some goal state right here at the origin. So this is the goal where we're trying to go. And say I have some initial condition here, x naught. What I can do, since this is a linear system, and I can just set up my cost function such that I want to drive myself to the center here. What I can do is that I can solve this QP, and this QP tells me that if I take all the things I'm supposed to, if I execute all these controls, I get the following history. It does this. So in a perfect world, I could just set up this problem, solve it once, and then just execute the control plan. So I solve for a bunch of x's and u's. I take all those u's and I just execute them one by one, and those u's should give me the next x's. So I solve that QP, it gives me a vector of u's, and I go and I just execute each u, and that's going to move me towards the origin. It's going to solve my problem. The problem is that in reality, I'm going to take one step of this, and due to errors in my actuators, errors in the dynamics, noise present in the environment, external factors, there's a million different reasons why we'd veer off this trajectory. And what's going to happen undoubtedly is that this first step we're going to take is going to take us somewhere off our plan. And so what you have to do is that, which is just fine, is just the problem is still well defined. I can formulate and solve this problem again, but the problem is that every time I take a step and I'm a little different, I have to reform and solve that problem. So solving explicitly for these controls u at every time step is wasteful when I've found that a feedback control policy described by k can do this same thing. And this is kind of like the main reason why finite horizon LQR, that control gain k, is so popular, because it's going to be globally optimal for linear systems with an infinite horizon. And I'm going to say that no matter where I am in the state space, no matter what happens, if I just apply u equals negative kx, I have my optimal policy. So we'll see here is that we kind of have two options. I can either solve the QP, or I can be smarter about it, and I can say, here's my k. And then for the infinite horizon case, so this is I'll do k, and then I'll make a note here. This is from Riccati. So at every time step, I can either solve the QP, or in the time varying case, I can solve the Riccati equation. I can get a new gain k. Or what I can do is, here's my infinite horizon. So infinite horizon LQR. And this is a no-brainer. I should just always do u equals negative kx every time. And this k is going to be from some discrete LQR function. It takes an a, b, q, r. And this function you'll see in MATLAB and Julia. So I think that tells a pretty solid story. So another cool thing that we can talk about here is that another benefit of having one of these feedback policies is I don't just have to drive to the origin. I can drive to wherever I want to. So if I want to, make this robot do a circle around here, I can just set that tracking point to be around the circle. As opposed to doing u equals negative kx, I could do u equals negative k x minus x goal. And I can now drive my system to any x goal that I want to. So this, I think, deserves like a little more of a story. So what we'll do here is that we're going to talk about basically why we can do this. I'm going to do some change of coordinate tricks that are going to be super useful for general homeworks and stuff that you'll do. And so what I'll say is that imagine I have some linear system. Looks like our classic linear system. And what I'm going to say is I want to drive this system to some goal state that is like a nice fixed point. So there's a spot in my state space where I have X and U, and if I get there, I can hold myself there. So that tells me is that X goal equals A, X goal plus B, U goal. So what I've done here is I say that I have a state and control X and U, and I know that if I'm at this spot X goal in the state space and I apply X goal U goal, I'm going to stay there. So imagine if I'm like a double integrator, like if this I could equilibrize about nothing. I could say, I have zeros just hanging here. So I have this X goal, and me writing out like this just shows me that it's a fixed point. And what that just means is that, or if you remember, a fixed point is like X equals f of X. So our fixed point is us saying that xk plus 1 equals xk equals f of xk. So this just means like what we have here is a fixed point. It's like a stable equilibrium point. And now what I'll do is I'll define a new coordinate system. I'll define, I'll call them tildes. So x tilde is going to be x minus x goal. I'll drop the goal and say g. U tilde equals u minus ug. And now what I can do is I can kind of like write out the dynamics in a way that should be somewhat familiar. So if I want to write out x tilde of k plus 1, what I have is I have x k plus 1 minus xg. So nothing crazy has happened so far. And all this is a of xk plus b of uk minus xg. So I just expanded out this to be this. I'll do some color coding here. And now let's expand out the second part. So I know that xg is a fixed point. And what I said was that x goal equals a times x goal plus b times u goal. So I know that I can, if I have an x goal, I can substitute out for this right here. I'll do this. Expand this out. Minus a x goal plus b u goal. And this just gives me the following. Which is xk plus 1 tilde equals a of x tilde k plus b u tilde k. So what I just showed is that for any arbitrary linear system, if I can define some equilibrium point that I want to drive my system to, an x goal and a u goal state, such that I had this nice, it's once I'm at that point, this is like a stable point. So actually I am able to control my system around this point in a stable fashion. I can define what these x goal, u goal are, and then I can just drive my system to that by looking at this new linear system. So if I were to tell you that this is my new linear system, I say, just assume that these tildes, this is just the new variable that I'm considering. Here's my A and B matrices, which are the same as before. And I would go and I'd solve for my LQR gains. So K equals D LQR of A, B, Q, R. So I solve for my LQR control gains. And now this tells me the following. This tells me that I can do U tilde equals negative K X tilde, right? So nothing I've done from here to here is like a big leap. I'm saying these X tilde, U tilde, these are my new variables that I care about. I define my LQR problem on these, which is totally fine because my dynamics, as you've seen here, are in the form that we like them. And the optimal feedback policy just ends up being this. And so now what we'll do is that we'll substitute in the original variables that we have here back into our new system. And what we'll see is that we now have U minus U goal equals negative K X minus X goal, which means that U is just equal to U goal minus K X G. So the whole point of that thing I went through is I said that if we define a new point that I want to drive us to, so I have this X goal state that I want to drive the system to, and I have a corresponding X goal, U goal, such that once I'm there, I can stay there. And then I can just define this new coordinate system with these tildes, where everything is with respect to these goal states. And then I can write out the dynamics, and I can see that I get the same form, so the same A and B I had before. And now, because my dynamics are written out in this way, I can just use LQR as normal, nothing changes. If I call my discrete LQR function, I get my gain matrix K. This gives me U tilde equals negative K times X tilde. And I can just substitute back in the variables. And now what I can see is that if I have a feedback gain K, and nothing here was specific to the tildes, right? So I can solve this for any, like it does not matter what the X goal, U goal are. I can just solve for this control gain. All I need is the ABQR. And then this tells me that I can drive my system to any arbitrary X goal, U goal just by doing this. And this is why this is so powerful, because I don't have to plan anything out and then do it every step of the way. I can just implement this feedback policy with a constant gain K, and I can just move around what my X goal, U goal are, and I can drive my system to those points. And I wrote this earlier, I said, it's so great because this K that we get from infinite horizon LQR, I can just use this K, just drive my system to any goal state, and like you totally can. And this is kind of like the formalized reason as to why we can do so. So now imagine if I thought about this in terms of a slightly different coordinate system that's going to be more useful to us when we start moving on to nonlinear systems. So what we'll see is that if I had defined the system just a little differently, and imagine I still have this X goal, U goal. So I still have a X goal plus B U goal. I still have this X to UG. Now what I can say is that I'll define a new system where I just say that X equals X goal plus delta X. So the old
Kevin?
Yeah.
May I ask a question?
Please.
Okay, so when we solve for the optimal feedback policy K, so it does not depend on the state.
No.
But so does that mean that you can reuse the K that you solve?
Yeah. So the idea is that if I'm doing infinite horizon LQR, I can solve, all I need is the ABQR. So I just need this right here. And there's no information here that I contained about my current state, right? All I did was I solved for the optimal feedback gains. So I have a feedback policy. I solved this once, like I solved this once offline, and I just like put the K on my robot or on my system, and it can just, no matter where the state is, it'll always be acting optimally.
Okay. And let's say your goal change. Do you have to, you have to solve again the LQR problem, or you can still reuse this?
Yeah, so this is like why this is so magical.
Okay.
Because I solved this gain K, and this is going to apply anywhere in the state space, and it can drive me to any goal in the state space. So this, like, basically, we were really strict about our assumptions at first. We said, the system, the dynamics have to be linear, the cost function has to look in a certain way. So I was very specific in the beginning, and I made a bunch of like assumptions of how our problem needs to be. And the reason we do those things is because we get this like magical result where we have to solve once for a control gain K, and this applies anywhere in the state space and can drive us to any goal, assuming that you can actually like stay at that goal. Like assuming that the goal is achievable, this can drive you to that goal. And this is why this is like, really kind of like the best control answer for a lot of simple systems. For really complex stuff, this won't work. For very nonlinear stuff, this won't work. But it's pretty amazing how well this works in a lot of cases.
Okay, but so you cannot implement this online, right?
You can, yeah. So if you wanted to, you could solve, every single time step solve for this, but you'd be solving for the same K every time.
Okay.
Like there's no performance penalty to solve this thing once and just like letting it go. So looks like I got a quick question in the chat. It says, what happens if A and B are time varying? So if they're time varying, and I don't know what that, so I guess there's a few different ways you could answer this question. So if A and B are time varying, I cannot solve for just one policy K. What I can do is I can do my time variant LQR. This is where I solve for, so actually I'll write this out explicitly. So imagine I have a time variant LQR system. Here's how like that control call looks. time variant LQR is going to do the following. It's going to give me, I take in my A's, my B's, and then Q, R, Q final. And this is going to give me a bunch of Ks. So say I was trying to run my robot for like a 20-step program. What I would do is I'd do the time variant LQR. I would do the Riccati recursion that Zach went over on Tuesday. So I do this Riccati recursion and I get Ks for every single time step. And then online, I just implement that control call. So it's like, U of K equals, actually, I'm not going to use K. I'm using K too much. So U of I equals negative K I times X of I. So here what I can do is if I have time varying A and B's, this means that I have some finite horizon problem. So I'm looking at a 10-step problem or a 100-step problem. And what I can do is I can give it those corresponding A's and B's for that time span that I'm looking at. I do the Riccati recursion, and this gives me a bunch of Ks. It gives me a new set of feedback gains for every time step. So at time step 1, I have K1. At time step 2, I have K2. And this will give me a control policy where I say that U at time step I is going to be equal to K at time step I. So it's one of these that I got times X at time step I. It doesn't matter. Again, I solve this thing totally agnostic to what the current state was. All I'm doing is I get feedback gains, and I'm looking at the X as it comes in and applying my feedback policy. So if A and B are time varying, I solve for a bunch of Ks and I execute one at each time step. Does that answer your question?
Yes, thank you.
So that means that you have to know all the different A and B's beforehand, right?
Yeah, it does. So if you remember, if the way we had this system, I guess like the way that we argue that we need the system to look is it needs to look like the following. It needs to be X K plus 1 equals A as a function of time, XK plus B as a function of time, UK. So you're right. I need to know what these A's and B's are going to be at certain times. So these can't, like, if these A's and B's are going to change depending on where I am, then my system is no longer a linear system because these A's and B's are functions of X and U. And what I said is that in order for this whole thing to work, A and B must only be a function of time. It can't be a function of X or U. So to answer your question, I do, if I'm doing finite horizon LQR, where I'm doing time variant LQR, so I have a different A and B every time step, I need to know what those things are going to be ahead of time. And I can do so because what I assumed is that my system is only going to work if I know these A's and B's as a function of time. They can't be dependent on state or control. If they are, then our system is not linear. Does that make sense?
Oh yeah, and so since they're depending on time, I mean, we can compute them beforehand then.
Exactly, yeah.
Thanks.
Exactly, yeah. So I think like a good example. So imagine if I was like, doing some robot demo where I had my robot like go from point A to point B, and I'm sitting there on the floor and I compute offline what my A's and B's are going to be at every time step. And I go and I plug this into time variant LQR, I get a bunch of Ks, and I send all my Ks to the robot and I tell it at time step 1, execute the feedback policy where I have K1, time step 2, execute the feedback policy where I use K2. And so that kind of stuff you do offline and then hand to the robot. You can also, these things, like these are all fast things to solve, and you can totally solve these things online. You could do some like fancy prediction stuff where you try and predict what your A's and B's are going to be and resolve this problem at every time step. These are all things that people have done and do all the time, and none of this stuff is that expensive to do. But the point that I'm making is that for the infinite horizon case, where I just solve for one gain K and then just ship it off to the robot and let it handle all the stuff, for a lot of simple systems, that's enough and that works. And it's, as fast as anything could be. All right, so now I'm going to go through some delta notation, which for the rest of the homeworks of the year, I'm going to be super big on this delta notation. And Zach uses this in class, and he kind of like assumes that everyone knows it. And some of you may know this, and that's great. But I'm basically just going to formalize it and write it out explicitly in case you haven't seen it before. Then we can know like we're all on the same page. So same thing as before, where I say x goal equals a times x goal plus b times u goal. It just means that our x goal, u goal, this is a stable equilibrium point. It's a fixed point. And then I say that I define this new delta such that it's u equals u goal plus delta u. And all this means that, like, if my desired u is like 5 and my current u is 10, that means my delta u is 5. So like, this is a very simple example. I'll say it. Imagine if this was it. So it just like gives me a way to describe delta u's that are like referenced about some UG. So once I have that, I can kind of rewrite everything. So now I can rewrite my dynamics. I'll see x k plus 1 equals x goal plus delta x k plus 1 equals, and then here I'll do I think, what is the best way to do this? So I guess I'm gonna like try and color code this out so it makes a little more sense. So we start out with our classic dynamics. And now I'm going to start doing some substitutions. So I did this went to here and then went to here. And now this is a times x goal delta x. So this is this plus b u goal plus delta u. And that's this. So is that clear, like where I substitute all these things to get? I just started with my initial dynamics, expanded this thing out using this stuff. I basically just substituted in the x's and the u's, and what this gives me, it gives me the following. It gives me x goal plus delta x k plus 1 equals, and now I'm going to like try and separate these things out. So I'll say a xg plus b ug. So this is me just pulling this term and this term out, plus a delta x plus b delta u. And now what I can do is that what I wrote before was that this is stable. So xg ug is just going to return xg. So I can use this fact, and now I can just say, okay, well, that means that I can just cross out this. This gives me delta xk plus 1 equals a delta xk plus b delta uk. And here we have our linear dynamics that are written with respect to our deltas. So this gives us a way that I can define any point that I want to that is stable. I want to drive the system to define these deltas with respect to that point, and then I still have my same linear system, which means I can still use all my LQR tricks. So now I could do, what we just did before. I could do k LQR a b q r. And I can just say delta u equals negative k delta x, and I can substitute in there and get my policy. And this is another way of reframing the exact same thing I did earlier, where I define like the notation with the tildes. I just used deltas opposed to the tildes in the way I structured it. And the reason I did this is because when we do nonlinear stuff, which I'm about to do a quick example of, we're always going to use deltas. So opposed to doing like the weird, like introduce like x tilde, u tilde, everything will be deltas with respect to some referenced linearization point. And so now I'm going to spell this out really clearly. So now we have extension to nonlinear. So now say I have a nonlinear system. And what this tells me is that I'm just going to, this is as specific as I can get. I have this right here. And then what I want to do is I want to linearize this system about some point. So I'm going to say, okay, imagine I have imagine I have X bar and U bar. This is a fixed point. So that just means that X bar equals F X bar U bar. So say that I had a stable point if I want it to be. What I can say is I can now say that if I want to approximate these dynamics with a first order Taylor series, I get the following. I get, so originally I had xk plus 1 equals f xk uk. And now what I'll do is I'll say, now I'll take a Taylor series. Now I think the xk plus 1 is going to be approximately, and I'm taking this Taylor series about the linearization point x bar u bar plus df dx evaluated at x bar u bar x minus x bar plus df du at x bar u bar u minus u bar. So I didn't do anything crazy here. All it is that this is the first order Taylor series of this function f about the point x bar u bar. Okay. So now what I can do is now I can define my deltas. And now I can say that, okay, well, I don't want this in terms of x's and u's. I could do that if I wanted to. This is a totally fine way to write this. So I'll do this. This is option 1. This is a totally fine way to write down this linear system. Alternatively, I can do the following. I can say that x equals x bar plus delta x, u equals u bar plus delta u. And now I'm just going to substitute in the system. So now if I substitute back in here, I'm going to get my second form. This is I'll do a quick copy of this just so it's all on the same page. Now I have the following. Now I'm going to substitute in here, so I get x bar plus delta xk plus 1 is approximately fx bar u bar. And just to do some shorthand here, I'm going to call this thing a bar and this thing b bar. This is just my dynamics Jacobians with respect to x and u taken at x bar u bar. And then this will be plus a delta x plus b delta u. And now we'll see something interesting. So I said this was a fixed point, right? I said that if I took in x bar u bar, I'd output x bar. So this tells me that I can cancel these two things. I can cancel this, I can cancel this. And now I just have delta xk plus 1 equals a bar delta xk plus b bar delta uk. And this is option 2. This is the one that we'll be using quite often. So option 1. So all I did was I defined an x bar u bar, and I said this is an equilibrium point, so it's a fixed point in discrete time in our state space. And I took the first order Taylor series, and I saw that if this is in fact a fixed point, these things drop out, and I can now write my linearized dynamics about the x bar u bar in this form. So throughout the class, we'll hear Zach say things like, oh, we'll linearize about this point and like, extend the linear stuff to this nonlinear system by linearizing about that point. And I feel like sometimes I feel like we need to be like a little more precise about like what we're actually doing. So what we are explicitly doing is we are taking a point x bar u bar, and I'm forming a first order Taylor series of my nonlinear dynamics function. So I just expand this thing out using the following way. And nothing I did here was crazy or rule breaking. I just said that I'm going to introduce these new coordinates where I have deltas, where I just say that the current value of the state x is going to be defined as x bar, so the point that I'm linearizing about, plus some delta x, and the same is true with u. And then I wrote out the first order Taylor series. I just substituted some things in here, and now I see that if I linearize my nonlinear system about some point, I can get to a decent approximation depending on how a nonlinear the system is. I can say that, okay, here is my like locally approximate linear model of this dynamic system about this point. And the reason why this is so powerful is you're going to do a homework question on this, but Imagine if I had a cart pole. So if you guys have seen the cart pole is like a box that has this thing and it can move back and forth. This is a super nonlinear system. The idea is that you can like swing this thing up, such as swings up and goes up. So what I can do is I can take this system about the point where it's standing upright, and I can linearize the system about the point where it's standing upright. And this can give me a control law, such that if I nudge this thing, it'll like help itself. So if this isn't super clear, you're gonna have a homework question that's gonna kind of like walk you through this step by step. You're gonna take your nonlinear dynamics, you're gonna linearize them, you're gonna form your linearization that is actually accurate. And we're gonna decide which point that is. And so for the cart pole, it's gonna be when this thing is swinging upright. And then now that we have this locally approximate series of linear dynamics, we're just going to use LQR as if it's a linear system and just try it, and you'll see that it actually ends up working super well. And this is a more general result that if I have a system that can be like approximated linear about a certain point, and that just means that this first order Taylor series is actually pretty accurate, I can just take that linear system and do all the linear feedback stuff. So in our case, like we love using infinite horizon LQR. We can use infinite horizon LQR on this nonlinear system about this linearization point, and it'll just work.
And Kevin,
yeah.
And what happens if your LQR just drive you outside the domain of validity of your linear system?
So that is totally possible and certainly happens. So when that basically that LQR feedback law, what we said is that in a linear case, this thing is globally optimal, no matter where I put you in the state space. So yeah, it's a good thing to draw out. So in general, imagine this is my like state space, right? So I have like x1, x2, and I have a 2D state space. What LQR told me is that LQR is good for a linear system. LQR is good everywhere. So LQR is globally optimal. And then what I said is that, okay, well, let's linearize about some system. So now imagine that this is like my delta state space. Delta x, so I don't know why I switched the order of these things. Let me write this out better. So x1, x2. So now imagine this is like our delta state space. So delta x1, delta x2. Our LQR control law applied to this nonlinear system by treating everything at the level of deltas is really only going to be good for a spot in the state space that's close to where we linearized. So this thing is only really going to work when the linearization is accurate. And since I formed a first order Taylor series to linearize this thing, there's all the higher order terms that I'm ignoring. And what that means is that my linear feedbacks, my linear dynamics that I wrote right here, where here I have linearized about this point, this will only really be accurate for small perturbations. So it's some region that's close to the origin in our delta state space that this nonlinear LQR is going to work. And so I'll do, write this out. This is LQR on nonlinear system. It's only really going to be accurate like around here. So yeah, it's totally possible that your robot, for whatever reason, like on model dynamics and whatever, it could leave this point in the state space. And now it's in like a dangerous territory where now my LQR assumptions that I'm applying on this nonlinear system don't work that well. And the system like could like totally fail. That's like completely a possibility.
Okay, and so that's you assume that case if our initial condition is outside this domain, but can the LQR just drives you outside?
No. So again, this is all, so since it's nonlinear, I can't guarantee anything about the accuracy of this linearization.
Mm-hmm.
But basically, if I start this system like right on the origin, LQR will not drive me away from it. But there's a chance that if I start somewhere here, maybe the linearization is already inaccurate at that point, and the LQR control law is going to be unreliable, and then it could drive me out of there. But
okay.
in general, what happens for all intents and purposes when we apply this thing on nonlinear systems is that like we're going to have some region where the controller is totally fine, and it's always going to stay inside that region. So if you imagine if I do the cart pole swing up and I swing this thing up, this region is like relatively big in this case. It's maybe like 20 degrees, like one way or the other. So you can see that you can like move the system around a bunch, It just it's going to recover from everything. So normally it does a pretty good job of like staying like within this point. It'll get like little disturbances and stuff that'll like move it out of the point, but it'll do a pretty good job with the controller of like keeping everything like in that spot. But generally, unless it starts somewhere like very far away, the LQR controller will never drive it like further away from where it wants to be.
Okay. All right, thanks.
Yeah. So that is all I had planned for today. It took a little longer than expected. But if you guys have homework questions, I'd be happy to like look at some stuff right now. Go ahead and stop the recording.